All right, welcome, folks, to this talk on Apache Hudi clustering to make queries faster on Presto. Next slide, please. So let's take a look at the agenda for today. First, we'll discuss some basics about Hudi. We'll talk about how we are using to evolve our data lake using Hudi. We'll dive into why we built clustering and how it's helping improve the performance of queries on Presto. And finally, we'll briefly touch on some of the future work. Next slide, please. Right. So yeah, my name is Nishith. I am an engineering manager at Uber. I manage the data lake team and been with the Hudi project since the beginning. My team works on many aspects of the data lake, including storage, table management, data consistency, and more. And I have my colleague here with me, Satish, who will be covering the second half of the presentation. Next slide, please. All right, talking a little bit about Hudi. Hudi is a data platform technology that provides several functionalities that one needs to manage and build a data lake. At its core, it's a storage library that is used to address a variety of requirements that are needed by the data lake. Some of the notable requirements are, supporting efficient ingestion of database change logs, which means supporting inserts and update type workloads, removing, and deduping any duplicates from log events, which would be, millions of events at a second. Data lake in general, needs to provide some efficient storage management. All of the tables and data sets. But he provides many table services to let us manage this, some of which we'll discuss in a later slide. We want transactional rights, some kind of asset semantics on the data lake. And we want to be able to provide some tight SLAs on data freshness, whether it be for faster, for derived or raw data. And we need primitives for that. Beyond that, there are some other requirements such as compliance, unique key constraints, and late handling, all of which we use Hudi to help solve. Next slide, please. So some facts about Hudi at Uber. We use Hudi to manage about 250 petabytes of our transactional data lake. That amounts to about 8,000 tables, ingesting about 500 billion records a day. So we're running all of these at pretty large scale, and as a result, obviously our queries are also running at a large scale across these data sets. Next slide, please. All right, so here I'd quickly like to talk about how we are, reimagining sort of data lakes using Hudi at Uber. In a canonical data lake architecture, all incoming data into the lake or warehouse, you may have some source, typically like Kafka, and then based on use cases and preferences, you may choose a batch or streaming-oriented model. Now, this data ends up landing in, data lake tables managed by Hudi. Hudi internally has a transaction log, pluggable primary key indexes, and a bunch of base and delta files together which support the features that we discussed earlier. Now, this data is available to be queried by Presto and other query engines, right? Generally with the help of a metastore. This is pretty standard stuff. Now, some of the problems we face with this architecture are, who will manage sort of the file counts of increasing number of file versions? How do we archive metadata and data that is unused? How do we keep the number of data files in check? So this is where we supercharge our data lake at Uber with Hudi. It supports a number of inbuilt table services that Hudi manages. And these integrated table services include cleaning, removing unwanted and failed files, compaction that keeps the number of delta and base files in check by intermittently keeping them compacted. And this gives a lot of flexibility for us to manage these tables. So recently, we've started to dig deeper into how can we help optimize queries on Hudi-based tables. And as part of this effort, we contributed a service called clustering that is meant to optimize the data layout and make it suitable for query patterns. And so, in the next rest of the slides, we want to explore how clustering can help optimize the data layout. So before we get there, I quickly want to go over sort of the current state of integration between Hudi and PrestoDB. Just as a disclaimer, the next slide will have some jargons, which is pretty related, which may not be familiar. But if you want more details, you can go and visit the Hudi Apache org website for more details. Next slide, please. So in its current state, we have a copy on write on PrestoDB. This storage format in Hudi is meant to be read optimized. It provides all of the popular features that you would want, like column, vectorization, predicate pushdown, etc. And both kinds of like queries are supported. Point in time queries as well as incremental queries. This integration also supports merge on read tables. So this storage format is optimized for write throughput and meant to reduce ingestion latencies. Obviously, these tables also run compactions, which help to provide vectorizations and predicate pushdown primitives on columnar data. Next slide, please. So yeah, at this point, I'll hand it over to Satish to talk to us through the use cases and solutions that led us to think about clustering. Satish, over to you.
Hello, everyone. I hope that gave a good understanding of how Presto and Hudi operate together. In the rest of the presentation, I'm going to specifically talk about two important goals for this work. First, we want to reduce our storage and query costs to improve utilization of Presto clusters. Next, our users request for fast data. This means two things: low end-to-end write latency to make the data available as quickly as possible and improve freshness. And second, once the data is available, users also want faster query response times. To satisfy these requirements on our transactional data lake, we needed to develop a new framework for rewriting this data. Let me explain a little bit more on why we need a new framework for writing the data. So at a high level, there are two important components in the data lake. One is the writer, the data ingestion component that writes data to durable storage, and the query engines that read data from this store. Now, both of these components are optimized for different things. I listed two important trade-offs here on the first column: the data locality and the file size. As you can see in the table, the data ingestion typically stores data based on the arrival time, whereas query engines work better when the data queried often is co-located together. Similarly, data ingestion prefers small files to improve parallelism and thereby increasing freshness. But query engines typically performance degrades when there are a large number of small files. So with that context, I want to introduce Hudi clustering. Clustering is a general framework we built to change data layout based on query patterns. As Nishith mentioned, we have thousands of tables, and we want to provide like a flexible framework that optimizes the data layout for each of these tables. So clustering provides pluggable strategies to change or rewrite the data on the data lake. We provide two strategies in the open source. The first one is sorting strategy. This is the main purpose of this strategy is to improve data locality by sorting on user-specified columns. This strategy can also control file sizes to work around small file limitations, as mentioned earlier. We also provide stitching strategy in open source. This, as the name indicates, this is useful primarily for controlling file sizes. So this assumes that the data locality is already taken care of or not as important for the use case during ingestion. This strategy is often used for like micro batching kind of use cases where primary goal is to improve freshness by writing data in small files first. Small files are then stitched together using a clustering framework to improve the query performance. Clustering also allows for flexible policies. For example, it is easy to configure the partitions that we want to rewrite in each iteration. We can also choose to use different data layouts for different partitions. This may be useful if query patterns evolve over time. For example, new partitions can be sorted based on most frequently used predicates in the last few days. Clustering can also can be configured to run at different granularities. So let's take sorting strategy an example. If we pick global granularity, all data in the partition is read back, sorted according to the specified columns, and rewritten to the same partition. If the local option is picked, then sorting is done on an individual file level. Users can also specify like custom plans and divide files in the partition into multiple logical groups based on either file level metadata or table level metadata. The other nice thing is clustering adopts all the Hudi transactional asset semantics. So it provides snapshot isolation and time travel for improving operations. So this means you can restore and roll back a table to a previously well-known state very easily. Hudi clustering also updates Hudi internal metadata, and if an external index is configured, it invokes updates on the primary index. Clustering also adopts multi-version concurrency control used by Hudi. At a high level, this means clustering can run parallel to ingestion, and it can also run in parallel with other table services such as compaction and cleanup. Now let's look into how this sorting strategy actually helps improve query performance. I have an example query here to select two columns B and C from table T. The query also specifies two predicates on columns A and B. So in the bottom left-hand corner, you can see the storage layer where the data is organized in the Parquet columnar format files based on arrival time. To execute this query, a table span is required to fetch all rows from the table for columns referenced in the query. Presto engine then filters the data and projects the selected columns to satisfy or answer the query. As you can see, this is very inefficient as we need to fetch all rows from the table before we filter on the predicates. Now, Presto added a nice feature to do a predicate pushdown. So now let's look into what happens if this predicate pushdown is enabled. At the bottom, again, we see the storage layer where data is stored based on arrival time. Because data is stored on arrival time, it is possible that many data blocks still have at least one row that matches with the given predicates. So even with predicate pushdown enabled, in the worst case, we still need to process all data blocks in the Presto engine and then filter majority of the rows. Now let's look into the same query execution where data is sorted based on columns A and B. Because data is sorted on these columns, we can guarantee only a subset of blocks will have data for the specified predicates. Combined with predicate pushdown, this basically reduces the amount of data that needs to be processed in the Presto engine. So I hope that explains the importance of clustering at a high level. Now let's see how this works in practice. Here I have a sample query that is often used in a popular production table at Uber. I picked one partition from that table for this test. This partition has about 5 gigabytes of logical data. Sorry, I had to hide the table schema and columns, but the query translates to something like select two columns from the table where with the predicates on two columns. Now we ran the query without clustering, and you can see the query plan below. There is a lot of information in the query plan. The first thing to notice is we have a scan filter project operator. So this is basically taking advantage of the predicate pushdown feature. But because data is stored in arrival order, the query execution required fetching almost 2 gigabytes of data, as highlighted in the red color box here. Also note, majority of the rows are filtered by Presto query engine, and output contains only approximately 1% of the input. Right? So this is about 29 megabytes out of the 2 gigabytes input. Now this filtering is also expensive, and you can see the total CPU time spent on inside the query plan, which is about like 27 seconds. Here you can see the results of the same query after doing clustering. So basically, we use the same partition, but we sorted the data based on predicates used in the query, columns A and B in this case. So you can see the query plan again. You can see that the same scan filter project operator is used, but now the input is reduced substantially to about 180 megabytes compared to like the 2 gigabytes in the previous slide. Because of the reduced in the input size, the CPU utilization is also dropped substantially to about 7 seconds compared to the 27 seconds in the previous slide. Note that this is possible because both the features, predicate pushdown and clustering, are used together. So this slide kind of captures summary from the previous two slides. As you can see, there is order of magnitude difference, performance difference with clustering. Both input data size and input rows are reduced by a factor of 10. Because of that, there is 4x reduction in the overall CPU cost for executing these queries. Just want to highlight that this again is run on a small partition. But I think we're in the process of enabling this feature on large data sets, and preliminary results show similar order of magnitude savings in CPU utilization. Also, want to highlight that because of the reduction in the input data size, we're able to make the queries faster. So we're able to reduce the query latency by about 50%. Now, this slide captures how we run clustering in production at Uber. At a high level, we have ingestion pipelines that write data to Hudi table. This ingestion pipeline also uses a durable config store, basically storing YAML files to control all the configuration. Now, if we set up shadow pipelines to run this clustering, this shadow pipeline uses the same config store to fetch the metadata and the configuration for the table. And if clustering is enabled in the configuration, the clustering pipeline can rearrange data layout for selected partitions of the table. So both these pipelines can run in parallel, and they coordinate with each other while providing the same asset semantics of consistency and snapshot isolation on top of the Hudi table. So we have a lot of exciting enhancements that are planned on clustering. As mentioned earlier, we're in process of onboarding more tables onto the framework. And because the framework is designed in a flexible way to support different strategies, we are also using this for improving storage efficiency by exploring different compression algorithms. And we're also using this framework for encryption to support compliance use cases and column removal and some other use cases. Also, right now, clustering is provided as a library, so users still need to configure this shadow pipeline and do some work to tune the clustering job. So we want to make this as a service to simplify operations for table owners. This also helps us share like the common validation framework and monitoring framework across different types of related jobs. We are also working on adding priority and tiering. As I mentioned, there are multiple jobs trying to change data layouts across different tables. So we want to take advantage of this economies of scale and schedule these rewrite jobs when there is additional resources, when there's compute is cheap, as long as the specified SLA for rewriting is met. We also want to build a general framework to analyze all the queries on the given table and propose new data layouts. And once it goes through a manual review, we want to automatically onboard that the table layout and automatically do clustering to make operations simpler. And we are also working on adding secondary index support in Presto to improve query planning time. So right now, the significant portion of query planning time is spent on reading the column footers, reading the footers from the Parquet files. If we build a secondary index, then we can save up to 10% of the query planning time and further improve the CPU utilization. Lastly, we are also working on making enhancements to improve the efficiency of rewrite. So for certain strategies, for example, we don't need to serialize and deserialize all the contents in the Parquet file, especially for stitching kind of strategies. So we're working on removing this extra step and saving additional CPU resources. If any of this work sounds interesting to you, and if you're interested in contributing to Hudi or using Hudi, please reach out. The dev email list, or we also have a Slack channel on the website hudi.apache.org. And Uber is also hiring. Please reach out at datalakejobs@uber.com. Yeah, thanks for attending this session. I think we're a little bit early, but we appreciate any questions, comments, or feedback.
No worries. Thank you for keeping the session on time. Let's give people a couple of minutes to think about any specific question that they might have. Okay, I'll read the question out so other people can hear it as well. So, Hudi decides how to store the data during ingestion.
Satish, do you want to take?
Can you repeat the question? Sorry.
Yeah, it says Hudi decide how to store the data during ingestion.
Yeah, I think there are a couple. Yeah, Hudi controls the decision. I think there are two strategies here. We have basically provided some default partitioner strategies. So right now it controls the file sizing aspect during ingestion. But the key aspect here is that we want to make the data available as early as possible to the query engines, right? So we want to write the data to the data lake first as soon as possible. We have some strategy to control the file sizes, but right now, because the pattern of how the data arrives from upstream, we are not able to guarantee the data locality aspect. So that's why we are proposing this new, or we worked on this new clustering project. Nishith, anything that you want to add?
No, I think that just one more thing to add is you do have the option to manage the data layout as you ingest, but depending on sort of your use case, that may not be possible. And also a lot of times choices in the past of writing historical data in some format, whereas query patterns changing over time tend to sort of dissociate and cause sort of degraded query performance. And that's why sort of clustering comes in to help us.
Thank you. There are two more questions I see. The first one was around how big are AWS contributions, given that they are using Hudi internally. Have any insights on that?
I can take this one. So I think there are a bunch of people. There are a few committers we have from AWS who are contributing. They also actively work with us to, if AWS is upgrading some sort of Hudi version on AWS, then they work with us to understand the new features. But there are a few committers who from the AWS community who are on Hudi as well.
Okay. Sounds good. And I think there's one more question that came in. Is clustering available in the open source Hudi?
Yeah, the two strategies I mentioned, the sorting strategy and stitching strategy, are available in open source. And you're always welcome to contribute and add additional strategies that are specific for your use cases.
Okay, I think similar lines is Hudi in EMR includes clustering.
I think right now it's in progress. They're using an earlier version of Hudi. I think they're in the process of upgrading to the latest version, which should give these features back.
Okay.
Just want to call out that the general framework and everything is available in open source. The strategies are just something that are more use case specific, which in general use cases strategies are available, but other specific use case strategies are we keep it internally. For example, we also use clustering to serve some other use cases, such as removing older columns that are not being used anymore. We also use it to, we have use cases around time-based encryption of data at rest, and we need some sort of framework to perform time-based encryption of data at rest. And so you can plug in a strategy and do the same thing as you would do for other things. So that framework is available in open source. Strategies are available. Some specific strategies are where we keep it in.
Okay, thank you. Okay, we'll wait maybe another minute if there is a question. Otherwise, just stay online and see if there's something that comes up in the chat, either session or the event chat, and feel free to take the question. Deepthi has a question. What are the specific plans around indexing? Will create index statement be in Presto? Good one.
Nishith, do you want to take that one?
Sure. I think we are looking at some of the next sort of Presto integrations that we're looking at least from Uber's perspective, is eliminating the file listing. I think that work is already out, but some of the integration corners are to be sort of ironed out. So that's one. The second, once indexing is available, we will look at how to make create statements available, but there is no specific plan as of now.
Okay, Deepthi, I hope that helps. Okay, perfect. That sounds good. So I think we'll wrap up. This is, again, thank you once again for spending time with us and sharing details about Hudi. And you can turn the mic off or leave the session. I'll have the next two speakers come in for the lightning talk. Thank you, Satish. Thank you, Nishith.
Thanks, guys, for having us.
Yeah.